before break, we started talking about oscillations. I didn't assign a homework for tonight simply because I didn't figure people would really remember from Friday before break, especially when you've been studying for the exam we had yesterday. So there's no homework due tonight. There will be homework due on Friday, of course. So continuing on with a little review of what we did on Friday a week ago, we learned that for a simple harmonic oscillator, which is a special kind of oscillator, something that follows a sinusoidal pattern in the oscillations, you have a requirement that the net force on the oscillator is proportional, linearly proportional to the displacement from equilibrium, so that's what the delta x was, and lowering that a little bit, and it has that minus sign because it's restoring. So we have the two conditions, putting them together, you have to have a restoring force that's linearly proportional to how much it's been displaced from equilibrium. And the first example that we saw of that was a spring, had a mass up here hanging by a spring, I had oscillated up and down. We had Rachel time it so we can measure the period, and the period was the time for it to do one cycle. We defined the frequency is the number of cycles per unit time, so there was the simple relationship that frequency was 1 over the period, and we had those units we used for frequency of hertz, where 1 hertz is equal to 1 cycle per second. And then we had the angular frequency, which is exactly the same symbol as our angular velocity, because it functionally is the same thing. The angular frequency is 2 pi times the frequency. Why 2 pi? Because there are 2 pi radians in a circle. And so the units of this are radians per second. And so the conversion factor between frequency and angular frequency is very simple, just that factor of 2 pi. This is, we still did this, showing us the direction the force is acting, and using calculus that gives you the sinusoidal behavior for a simple harmonic oscillator. So the simple harmonic oscillator, why is it important? Because it's sinusoidal in its oscillations. What makes it sinusoidal? Because you have the force restoring and linearly proportional to the displacement. I think this is the last review slide that I have from Friday. This was looking at the position versus time. Using what we learned just from the first couple labs of the year, we could take the position versus time and plot out what the speed versus time, and velocity versus time, and the acceleration versus time look like, and they're also sinusoidal. And using calculus, you can just take derivatives real quick and you get the equations for them. And we saw things like the acceleration is exactly out of phase with the displacement. So when you have maximum displacement, you also have maximum acceleration, but in the opposite direction, which perfectly makes sense. If it's pulled away from equilibrium and has a restoring force, the acceleration is going to have to be back toward equilibrium when it's pulled away from it. The final thing here, these are important equations that I repeat on the next slide. Based on the work on this slide, we had that the acceleration related to the displacement with this minus k over m, right? Acceleration is minus k over m times the displacement. And from the calculus work, it turns out that you have the acceleration is minus omega squared x. To make sure we're still all sane and with this, what did omega stand for? The angular frequency. So by just matching up those two equations, we can see that the angular frequency is equal to the square root of k over m. So if I have a simple harmonic oscillator, then there has to be a k, a constant to tell me about how strong the restoring force is. And if I have a mass oscillating, I can find what that angular frequency is just by combining them. So it's very simple to find the angular frequency if you know the spring constant, you know the mass, or of course, you have just a few variables, you know the mass and the angular frequency, you can find the spring constant and so on. Very simple relationship. Now I want to turn to the pendulum. Right? You might remember in the lab final it said find 2 ways to find the acceleration of gravity, and I only graded on one because the only way you knew was dropping something. But here's the second way with the pendulum. So the first thing about a pendulum is we need to check to see if the force is going to obey the required situation for a simple harmonic oscillator. So over here, there's the requirement. The force has to be linear proportional to the displacement. So if I look at the pendulum, the first thing I have to say is, well, what is the displacement for the pendulum? It's swinging back and forth. If we were in the normal classroom, I would have the bowling ball hanging here so we could do some fun things with it. But, we're here, we got nothing. So, hand waving and pictures. The displacement for a pendulum could be measured one of two ways. One way you could measure the displacement is measuring the angular displacement. That is, you could just measure the angle from vertical and say that's the displacement. It's not linear displacement, it's angular, but you could use that. Or you could measure the arc length, how far in distance it's moved away from displacement. So I have this done two different ways because there's the two different ways you can think about it. Now, just using our basic trigonometry relation, the arc length is always equal to the radius times the angle. So starting off, I'm just going to use the arc length as my displacement. So the delta x is L times theta. And then if I look at the forces acting on my bob, they're drawn in blue. What are the two forces acting on the bob? Okay, tension and gravity. Now, if I'm going to analyze this to see if it is acting like a simple harmonic oscillator, I need to look at the sum of the forces, right, the net force, that are in the direction that it can move. So if I look at the direction it can move, let's ignore this here, that's breaking tension into vertical and horizontal components, and look at this picture and say, what direction is parallel to the motion? Vertical, horizontal, or something else? In the picture right here. Vertical, horizontal, or something else? It's actually not horizontal. This mass is not going to go like that. It's also not vertical, it's something else. And so my directions I'm going to use for analysis is going to have one direction that's toward the center, just like we did with circular motion, and one direction that's perpendicular to that. And then I need to find which forces I have in the direction perpendicular to the center, right, in that x direction. So I need to take my forces and break them into components. So if I take my tension force, how much of tension is in the x direction? Okay, none. The tension is perpendicular to the x direction. It's parallel to my center direction. So the tension has no component that's in the direction it can move. Hence, it's just going to be countered by part of gravity. Gravity, on the other hand, I can break into components. So I'll put one dashed line going from the bob that's parallel to the radial direction, and one going from the tip that's perpendicular. And now with that triangle, here's my angle theta. And which part of the force, right, the force now would have to go like that to go from the start. Excellent. Go away. Collapse didn't do it. That did it. So if I look at these, which one, the adjacent side or the opposite side, is the side that is parallel to motion? Opposite. So that means this side here is going to be the only component of the two forces that's parallel to motion. That's going to be my force net. It's in the minus x direction, so minus the magnitude mg. And then if it's the opposite side, which trigonometric function do I have to use? Sine. So minus mg sine theta is that net force. So that's, of course, what I had written right there. So I broke the forces into components, found the net force in the direction that it can move, and then I say, does this here look like that? I can go one step further, because what was my actual variable that I said is the displacement? Delta x equals s, the arc length, which is L theta. So I could actually write this one step further as force net equals minus mg sine of parentheses. Since s is L theta, then theta is s over L. And sine is not the same as, sine of s over L is not the same as s. So that doesn't look the same. This one, linear proportional to the displacement. This one here, proportional to sine of the displacement over L. And so any first blush look at this says the pendulum is not a simple harmonic oscillator. But there has to be some relationship, or I wouldn't go into it, right? For small angles, you can use the Maclaurin expansion. You make a Maclaurin series, that's an expansion around x equals 0 for sine of theta. And you find that sine theta is equal to an infinite series, theta minus theta cubed over 3 factorial. Factorial just means take that integer, multiply by every positive integer down to 1. So 3 factorial is 3 times 2 times 1. Plus theta to the 5th over 5 factorial, minus theta to the 7th over 7 factorial, etc. Goes on forever, infinite series. And probably most people at this point are saying, okay, you can write this series, why would I care? Well, the reason to care is, if theta is small, then how would theta cubed over 6 compare to theta? Just to put this in practical sense, let's say theta is 0.01. What's theta cubed going to be? It's going to be really small. It's going to be 0.000001. And then you divide that by 6, that's even smaller. So if I have these two added or subtracted together, the one that's theta cubed is going to be insignificantly small compared to theta if I have a small angle. So only for small angles, sine theta is approximately equal to theta. So we call this the small angle approximation. There is a similar one for cosine theta. Cosine theta is approximately equal to 1 minus theta squared over 2 factorial, or over 2. And so we have this small angle approximation. Using that small angle approximation, if I come back, I can say, well, that's approximately equal to minus mg times s over L, or minus mg over L times s. Now, that is in the form for a simple harmonic oscillator, because it's now linearly proportional to the displacement s. And what's my spring constant, my K effective? If I just match those up, what is K going to have to equal? Mg over L. And that means omega, which is square root of K over M, is equal to the square root of Mg over L divided by M. What happens to the M's? They cancel. And I'm left with omega is equal to the square root of G over L. So the angular frequency only depends on the length of the pendulum and the acceleration of gravity. It doesn't matter what the mass is. Now, I do have to throw out some caveats. This simple pendulum, the simple and simple pendulum means that we have massless string Not perfect, but usually close enough, right? If I take a little iron mass and put it at the end of a piece of string, the mass of this string is very, very small compared to the mass of the iron. And so it's a pretty reasonable approximation. The second one is that it's a point mass. Point mass means no volume. So that's saying that my little bob down there at the end has no volume to it. Is that ever true? Not unless I have a black hole at the end of my string. Well, even then, we don't really know. Some people believe that it's, a true singularity, and others are all, there must be more physics that we just don't know. So it can't be true, but if the length of the pendulum is very long compared to the radius of your bob, then it's a fair approximation. So those are the approximations for this to be true. If you don't have those approximations, then you need to analyze this the second way I have shown here. The second way I have shown, you take the rotational equivalent of Newton's second law. The net torque is equal to I alpha. And you calculate the net torque about the center, so about here. So if I calculate that torque, I'm going to use this distance over here multiplied by the force of gravity to get that net torque. And, well, not times the force of gravity, times the vertical component. So that's shown right here. And then for the other side, it's I alpha, and I, if you have to use the real case, I is, spread out everywhere. You take the I of the entire object that's swinging back and forth about the pivot point. Now, one last thing I should point out. If you're doing it in the real case, those are not going to be the same L's at all. Because over here, it's going to be the distance to the center of mass. And on the other side, it's going to be whatever you need to calculate the moment of inertia of your physical object. So it's going to totally depend on its shape and how mass is distributed. So you have a more complicated situation for a physical pendulum. Physical pendulum means a real pendulum, the kind that actually exists. So if we talk about like our legs, as I walk, my legs are swinging. And as my legs swing, of course, I have, let's say, longer legs than Rachel. And so my legs have a bigger moment of inertia. And it actually turns out that it makes my leg swing slower than it would be for somebody smaller. And it turns out almost all animals have a similar leg swing to distance. I don't remember all the details, but there's a strong similarity in the speed that animals walk because of the leg swinging. If it's a bigger moment of inertia, like a longer leg, it's going to be slower that it's swinging because of this. So, I used to have a slide, but I didn't put it in today's lecture and didn't review it, that goes into the details on that. So we're not going to do problems with a physical pendulum, but you need to know that a physical pendulum exists, and that's the real equation, but it's more complicated because you have to use the distance to the center of mass for the torque side, and you have to use the actual moment of inertia on the other side. Now our first clicker question. Under what condition is a simple pendulum a simple harmonic oscillator? Okay, stop it here. Think about everyone's answered. And the answers we have are 11 said small mass, 3 said large mass, 10 said short length, 4 said long length, 13 said small amplitude, and 3 said large amplitude. We did not have a good agreement here, so turn to the people next to you and discuss with them, what did I say about this? What would the reasons be for whichever answer it is?
I said small. The conditions for you talking about is being small. So if not the neighborhood, it doesn't work. I don't think
And just I want people to have time to discuss it. Okay, let's go ahead and give it a second shot. So you can start answering now.
It just matters that we answer.
It does matter that you think about it too.
Well, yeah, but do you?
Yeah, you get points for answering. She's correct on
it's
that.
just for answering.
Yeah.
It's my own purpose.
Okay. This time we had a clearer picture. Whoops, 0. Okay. These two people answered. Rebecca Cunningham. Which one did you answer and what was your reasoning?
I put short length.
Okay, so you chose short length. And what was your reason?
My reasoning was that I thought I'd have a quicker restoring force because you'd come back to the center quicker than
Okay.
anything.
And what she said is true. If you have a short length, it will come back to the center quick. But that was not the condition where it fit to being a simple harmonic oscillator. To be a simple harmonic oscillator, we had to have sine theta is approximately equal to theta. So that this equation where we had sine, we could get rid of the sine and just have the force was proportional to the displacement. So the condition is that you have a small amplitude. What is the amplitude? Because I heard some people talking about that. The amplitude is how far, the maximum distance it moves from equilibrium. We talked about that a week ago Friday, so it may not have been right at the top of your memory there. So simple pendulum behaves like a simple harmonic oscillator only for small amplitudes. As you get to larger amplitudes, it starts moving away from it, so that if you get to the point where it's going in a complete circle, it's nothing at all like a simple harmonic oscillator anymore. If you go in a complete circle, you could have any frequency. So a simple problem, once you know what you're doing, to make sure that we do know what we are doing. So grandfather clock, you guys know the grandfather clock, you just have this big weight that goes back and forth, and you have masses that fall. So the grandfather clock, the way you wind the clock, so to speak, is you simply raise the masses. In terms of energy, what are you doing when you raise the masses? You're increasing the potential energy. And then those masses slowly fall and keep the pendulum swinging back and forth. So they transfer that potential energy into kinetic energy of the pendulum. So that's how they work. How do they keep time? They keep time because they use the length of the pendulum to get the period they need to keep time. And so if you need to adjust my grandfather clock is too slow, I'm going to have to adjust the length of the pendulum. And do I want to make the pendulum longer or shorter if it's too slow? That is, it's taking too much time to do one tick. I need to make it shorter because that's going to make the frequency higher. It's going to make it take less time per tick. So now that we have that, we have some information. We have the period is 2 seconds. What symbol do we use for period? T. So I have T equals 2.0 seconds. And then we have the pendulum bob has a mass of 150 grams. And I have an amplitude of 33 millimeters. And I'm supposed to answer. I changed the order of these, and now that I'm actually doing the problem, I realize why I had them in the opposite. Answer this one first. What is the length of the pendulum? Once we have the length, then we can answer, does this satisfy the small angle approximation? I changed them before class, and I was not thinking it through. So, as always, like you're solving a problem in your homework or on the test, you'll want to start with a diagram. So I have my pendulum out here, and that 33 millimeters, I don't care if you measure the 33 millimeters straight. Okay, I'm going to change the color. I don't care if you measure them like this or like this, because if the amplitude is small, those are going to be approximately equal. If the amplitude is large, they won't be approximately equal, but it'd be clear that it's not a small amplitude anymore. So that's why I don't care which one you use for your picture. We have the length and we had the period that I'm not going to write there, and the mass I'm not going to write there. So in order to calculate how long it is, what method am I going to go through? What would I write down for my concept?
What's the equation that relates the acceleration due to gravity to the period and the length of the pendulum?
Okay, we know that for a simple pendulum, omega is the square root of G over L. So given that, and that I know my period is equal to 2.0 seconds, if my period's 2.0 seconds, what's the angular frequency going to be? I thought I heard somebody say 5. Okay, that's a better answer. Okay, going through it long form instead of just knowing the answer because you can do math in your head. Omega is 2 pi divided by the period. And so Carrie said, well, I can do 2 times pi divided by 2.0 seconds, and that gives me pi radians per second. So omega was not hard to find here. And once I have omega, then I just solve my equation for L. So squaring both sides, omega squared is equal to G over L. L is equal to G over omega squared is equal to 9.80 meters per second squared divided by pi radians per second squared.
0.993.
0.993. And what are my units? It's just meters, because remember, radians is actually unitless, and the per second squared divided by per second quantity squared, the seconds cancel. And so we're left with 0.993 meters. How many significant digits do I have? Really only 2. So to correct significant digits, this is length is equal to 0.99 meters. And now we ask, is this going to be a small angle? What do you think? Yes is a good call, because I can say, well, if I put it the way I have drawn on top, if I use this distance here, Then I'm going to have tangent of theta is equal to my opposite side, 33 millimeters, over my adjacent side, which is 993 millimeters. Yeah. Notice I put the non-significant digit in so I don't throw away anything. And that's like what? 0.03 or so?
Yeah.
So having that 0.03 for tangent of my angle, what is the angle going to be?
Oh, it's 0.03 radians.
Oh, yes, that's also true, but it's 0.03 radians. Because for small angles, remember for small angle, theta is equal to sine theta. And cosine theta is 1 minus theta squared over 2. So if theta is small, that's basically 1. So that means tangent theta is approximately equal to theta for the small angle approximation. So they should equal each other. So we can clearly say 0.03 radians, that's a small angle. Now the tough part comes, how do you identify what a large angle is? Right? We can identify, okay, this is really small, but what makes it large? And you'll find different references. Some people will say, well, if it's less than 5 degrees, it's a small angle. Others will say, well, if it's 15 degrees, that's still a pretty small angle. It comes down to how accurate do you want to be, right? Because, you have deviation that gets bigger with angle, and you can actually go through and calculate what the difference between sine theta and theta is for different angles. And, if that gets up to being, more than 5%, you'd say, well, clearly that's not going to be a perfect match. But if it's 1%, you might say, well, that's fine. I can take a 1% error. And so there's not a clear cut and dried, this is a small angle, anything larger is large. It depends on your application, what you care. But for the grandfather clock, you have a long pendulum compared to the amount of motion, so it's always pretty much a small angle error. So, simple problem, right? Showing us how the grandfather clock works, a very practical thing. Speaking of practical things, when I went to the gym this morning, it was 34 degrees Fahrenheit out. I filled my car up with gas. And then I parked it outside, went into the gym for an hour, and came back. And where the needle had been just a little above full, it was now like, a 16th empty already. How did that happen? Because what? Not that it got warmer out. The gas, when it's dispensed from the pump, it's in a tank down below ground, so it was basically, 68 degrees Fahrenheit dispensed into my car. They don't want to dispense you cold gas because they would be giving you more gas per dollar. So it was put in as warm gas, but while my car was parked out there, the gas cooled, and just like the test question, what's up, Manawa? just like the test question, when it gets cold, that gas is going to shrink, and so the level drops in the tank, and it says, hey, you're not quite full anymore. And as I drove home from the gym, it started rising because the gas was warming up because heat from the tailpipe, probably. Okay, so another practical example of physics. Now, oscillators fundamentally are doing something with energy. They're fundamentally converting energy between potential and kinetic energy. So this picture looks exactly the same as the early picture that had force and was just looking at the force that was acting on it. But now we have the energy equations, and you see that when it's at maximum displacement, you have all potential energy. Oh, nice job. You have all potential energy and no kinetic energy. So your total energy is 1/2 kx squared. And I'm going to actually write that again so it's more legible. And I'm going to put A for the amplitude, the maximum x can get. I know the picture used a capital X for the amplitude, but I prefer A. That's what amplitude starts with. So my total energy in the first picture was 1/2 k times amplitude squared. In the second picture, it's at its fastest speed as it goes through the equilibrium position, and the spring is unstretched. So in this case, the energy total is equal to 1/2 mass times maximum speed squared. Now note the picture has minus Vmax squared. If I square minus Vmax, what do I get? Vmax squared. So the two things are identical. Why did they put it that way? Just to remind you that at this point in time, it was going to the left, which we're going to call the minus direction. If you look at this picture, it's going to the right, and then they don't put the minus sign in because it's going the opposite direction. If there is no friction, what can you tell me about the change in energy over time? It's what? It shouldn't. If there's no friction, if there are no non-conservative forces, then I should have no loss in energy, so my energy totals should equal each other. So that means if there's no friction, I should have the relationship that says 1/2 k times the amplitude squared is equal to 1/2 mass times Vmax squared, which gives me a simple relationship between the amplitude and the maximum speed. So Vmax, if I square root both sides and, of course, multiply by 2, now technically there's a plus or minus anytime you do a square root. So technically you have a plus or minus, and that's fine because you have Vmax in the positive direction and Vmax in the negative direction. What do we call square root k over m? Omega. So I could also write this as plus or minus omega times the amplitude. So from looking at the energy, you can see the relationship. What if I wanted to find the energy at some random location? What would the generic equation for the total energy be? You have a spring and you have kinetic energy, so I have to put those two terms in. So for the spring, I'll have 1/2 kx squared, and for the kinetic, I'll have 1/2 mv squared. And if my energy stays constant, that's going to have to be equal to 1/2 k times amplitude squared, or 1/2 m times Vmax squared. So I can take this equation and use it to solve for the position for any speed, or more useful, the speed for any position. So if I want to solve this for the speed at any position, I'll say all I did there was take this term, and rather than the 1/2 mv squared, and then I subtracted 1/2 kx squared and so then multiply everything by 2, because you would be an idiot to keep the 1/2. Okay, you wouldn't be an idiot, but you would be writing more than you need to keep the 1/2s there. Divide everything by m, and I'm going to have v squared is equal to k over m times amplitude squared minus x squared. Thus, v is equal to plus or minus square root k over m No, I put two separate square roots because I can simplify this plus or minus omega square root of a squared minus x squared. So using my energy equations, I can come up with a simple equation to tell me what the speed will be for any displacement, just as a function of the amplitude and the angular frequency. It kind of seems like magic to me that I can find a simple relationship like this, starting with my energy relationship. But it works, and life is good, right? Physics works, life is good. Physics did not work, life would be not so fun. Okay, you start answering now. Next clicker question. With what period should you push a swing to keep a youngster going? So, I take my grandsons at this point to the park, push them to swing. Do I want to push them with any frequency or any period, or only at the resonant period. The resonant period is every time they come back, you push them. Or any even multiple of that resonant period. So like if they come back every 2 seconds, I can push them every 2 seconds or every 4 seconds or every 6 seconds. Or any odd multiple of the resonant period works. So that would be, if it was 2, 3 times 2 is 6, 5 times 2. Or the last one, any multiple of the resonant frequency or period works. So this is your experience taking your relatives to the park and pushing them in the swing.
Like the same height or just swinging?
Height is not important here. Okay. Yeah, a lot more people answering now. But Manuel, you haven't answered yet, dude.
No, sorry.
You don't have your clicker? Okay.
I'm covered.
Oh, sorry, I just stopped. I thought you were indicating you didn't have it. Sorry.
It's okay.
Okay, the answers we got 6, 14, 9, 0, and 19. Now, let's just take this into our practical experience. Everybody here has probably gone to a park and pushed a younger relative in a swing, right? And so let's start off with, bad grandpa. Bad grandpa comes out and he's reading a book on his phone and he's just going like this and randomly pushing. What happens to, my 2-year-old grandson is Ashton. What happens to Ashton if I'm doing that? He may still, what? He may slow down or speed up. But we can be sure of one thing, he's going to be crying, right? Because he'll be going, bouncing around, and that's no fun. And he's not going to get to a really big amplitude because half the time, on average, I'm going to be pushing him the direction he was going. That means I'm doing work on him that's the push in the same direction he's going, a positive work, so his energy is increasing. But half the time, I'll be pushing when he's coming toward me. I'm going to be doing a negative work, taking away energy. And so he's basically going to be, doing this. That's not going to work. So I have to have a certain period. Not any period will work. So we can rule out the top one. You could definitely have the wrong period. So then resonant period. The resonant period is, all the rest of them have to do with resonant period, the time it takes to come back and go forward. So let's just say, for example, Ash is in here and I push him every time he comes back. So every time he comes back, I push him, I'm pushing the same direction he's moving. What's happening to his energy if I'm pushing the same direction he's moving? It's increasing. And so if his energy increases, what happens to the height of his swing? It gets higher and higher. That's my goal, right? I want him to have a nice big swing all the way up until the chains start, snapping, and then it's not as fun. You've all played with it. Okay. Now I have to keep pushing. Why do I have to keep pushing? Why can't I just walk away and let him swing? Okay, there's air resistance primarily. That air resistance takes away energy, so I have to compensate to keep adding energy. Okay, so we started, it would work fine if I pushed him every time he came back. What if I pushed him every 2 times? So I push him, he swings out, comes back, and I don't touch him, swings out, comes back, and then I push him the same direction he's going. What's going to happen to his total energy? Okay, it goes down a bit between my pushes, but when I push him, is it going to go up or down while I'm pushing? Up. So I am doing a net putting energy in. So as long as I'm pushing hard enough, that works. And you don't lose that much energy a swing. So I could push every other, and that would be just fine. What if I did every 3? I push him, out, back, that's 2, right? Out, back, and I push him again. Is that going to give him a net increase in energy or a net decrease? Okay, it depends on how hard I push. If I push hard enough, an increase. So 1, 2, or 3, if 1, 2, or 3 work, I covered evens, I covered odds. It's got to be any multiple of the resonant frequency works. Now let's look at a classic example. Now I have to give you the caveat, especially if you go online and you look for, physics, resonance, Tacoma Narrows Bridge, you'll find physicists who just get outraged that we use this as an example of resonance behavior, because it's a really complicated situation with the Tacoma Narrows Bridge. But if you just look at the basics of resonance, resonance is it has a certain frequency where it can oscillate. And if you push it at that frequency, you're going to constantly be putting energy in so the oscillations get bigger and bigger. That is what happened with Tacoma Narrows. So I'm comfortable using it, even if I have other people in this world who think that it's a horrible, horrible thing. So here is some video. There is no audio on this video. I used to have one that has audio. The bridge was built in the wartime, basically. They wanted to build it quickly. And soon after they built it, they noticed that even with mild winds, you would have oscillations here in the bridge. And of course, the kids, I'm talking to people your age, not my age, they thought, this is awesome. What better place to go out on a Saturday night than to be out there on the bridge just swinging along with Galloping Gertie, as they call it. But then one morning, and so I think these are all pictures taken from that morning. You can see there's a gentleman out there in the middle right now. He went out to check on the bridge, and it had different modes. It had up and down modes, and it had side to side modes, you see. He drove his car out there because he was a genius. He realized that this is not going to work driving the car on a bridge that swings so hard, so he got out and had to crawl his way back. There's in the audio that goes with this, he has a voiceover, and he says, he could hear the concrete cracking. His knees were raw from rubbing up, It's pretty funny, the drama. Yes, he's not drunk. When the activity got down, it stopped vibrating so much, he actually went back out there because he had his daughter's dog in the car. But things picked up again, so he had to come back in. I think that was him coming back in the second time that we just saw. And then eventually, it started oscillating really big, and we'll see that eventuality. Total collapse. And as soon as it collapsed, everything stopped and it got boring. I mean, you still had to have, friction take out some of the energy. So we'll have a picture from down the bridge here in just a sec so we can see, it buckling from the failure. Engineering students, this is your kind of problem. See, I wouldn't be all that happy out there on the bridge. Oh, yes, and he talks about being slammed to the ground. Well, sure. And then he ends his monologue by saying, and after all of this real tragedy, I think the thing that I feel worst about is I have to go home tonight and tell my daughter that her dog is dead. Along with his car. Okay. I like this guy here. He's all calm, whatever. All right. Enough on that. Back to the lecture. What was going on here was that you have, to the best of our understanding, the vertical wires are pretty much, if you look at them, similar to the strings on a guitar or a harp. You have wires of different lengths, and when air blows on them, you have vertices that form. That is, here's the wire, and when the air blows, it will come around and swirl on the back side. And if you look from the top, so here's looking from the top, the wind will come and either go like this or go like this. And so it forms vortices, and each time those vortices leave at a certain speed. That is, like every 2 seconds, the vortex will break away at a certain wind speed. You go a little faster, it'll break away a little earlier, so a little shorter time. And when they break away, depending on the direction that the vortex was spinning, it puts a force on it to make this string, this vertical support wire, oscillate. And so if the frequency of this Kármán vortex shedding, as they call it, matches the frequency for oscillation of that vertical wire, then the amplitudes get bigger. But if the amplitude gets bigger, you're actually going to be pulling up with that same frequency on the bridge. And if the bridge will oscillate at that frequency, then you're in trouble. And that's what happened here. So after a lot of analysis, they rebuilt the bridge, just making the bridge wider, which would make it have a lower frequency, and the problems went